I hear we're good to go, so I'm going to kick us off. Good evening, everybody. Thank you for coming to this Wisconsin Science Festival event. I hope that if this is your first event, you will check out many events this year. If it is not your first event, I'm glad that you're continuing to check out multiple Science Festival events. My name is Wes Marner. I'm the Director of Community Engagement for the Morgridge Institute for Research. We're one of the producing partners of the Wisconsin Science Festival, along with the Wisconsin Institute for Discovery and UW-Madison. And it is my pleasure to kick off our evening discussion with Dr. Michelle Thaller. So I'm not going to introduce Dr. Thaller. That is going to be the job of Dean Eric Wilcots, who is the Dean of the College of Letters and Science here at UW-Madison, and an accomplished astronomer himself, and a very longtime friend of the Wisconsin Science Festival. And you are in for a treat of a discussion this evening. I have to say that we just finished a dinner with Michelle with some graduate students and postdocs here at the Institute, and it was a delightful time at the table together. And while I've got the floor in a public way, I want to thank Dr. Thaller for offering, in addition to her time this evening that we're going to spend together, offering some of her time and insights to the graduate students and postdocs that are here at the university just to share advice and pathway and great conversation. So thank you for that. And with that, I'm going to hand it to Dr. Wilcots. Thank you.
Great. Well, thank you, Wes. Good. That's good. That's not on. Is this too loud? Is that blasting everybody? It's all good. Well, thank you and good evening. Welcome to this event of the Wisconsin Science Festival. It's always a joy, and one of the things we try to do with the Science Festival is blend together, as we don't do enough, science and storytelling. And tonight we are honored to welcome someone who embodies both of those things beautifully. Dr. Michelle Thaller recently retired from NASA after 27 remarkable years, most recently serving as the Assistant Director of Science at the Goddard Space Flight Center, which is NASA's largest base. She's also a Wisconsin native, born and raised in beautiful Waukesha, and her fascination with the stars began, as her mom tells it, before she could even walk. We might have to ask you about that afterwards. After earning her doctorate in astrophysics from Georgia State University and working at Caltech and NASA's Jet Propulsion Laboratory, Michelle became one of NASA's most recognizable science communicators, appearing on programs like NOVA, How the Universe Works, and countless NASA live broadcasts, including the launch of the James Webb Space Telescope just a few years ago. She's published widely in the Astrophysical Journal, earned multiple Webby Awards for NASA's online science content, and in 2025 was awarded NASA's Exceptional Achievement Medal, joining a distinguished group that includes Carl Sagan and the Apollo astronauts. So today, she continues her passion for sharing science through the Smithsonian Institution and as an adjunct professor right here at the University of Wisconsin. So please join me in welcoming Dr. Michelle Thaller.
How's that? Is that good? Yes. All right. It's a pleasure to be here tonight. Like I said, I actually left Wisconsin in 1988 when I went to college at Harvard University. And I've just moved back. And I love Wisconsin, and I am so incredibly proud of the universities we have here. The University of Wisconsin is a world treasure. And I was here, literally, I'd come here when I was 16 or 17 years old to go to a Badgers game, and I would try to pretend like I'm a college student, things like that. So, it's really a wonderful chance to come back to a little bit of my past. But the way that this evening is laid out is most of it, which I love best of all, is going to be for questions and discussion. But they've given me like 20 minutes to talk about science. And that's sort of like torture for me, because what am I going to say in 20 minutes? When I was Assistant Director of Science at Goddard, I was involved in the communications for at any given time, NASA usually has about 100 missions doing science. Earth science, science of the sun, astrophysics, planetary science. And the one that they chose, I actually gave them a list of missions that I could talk about, was talking a bit about finding the origins of ourselves and our biology even in space. And I wanted to back up a little bit before I talk about that. This is a relatively new picture from the James Webb Space Telescope, one of the missions that I've been working on since the mid-90s in some capacity. And it launched in 2023. And to set the stage, astronomy often seems like the study of things that are distant, things that are so far away and so big, they really don't have much to do with us. And nothing could be further from the truth. And this is where the storytelling and really letting people understand what the value of science is and the value of yourself. This picture is a cloud in space that is currently forming thousands of new stars. And you can see up here, there's a cluster. Oh, there we go. Yep, there's a cluster of newborn stars here. And they're putting out so much heat and light, and there's actually a wind of particles, protons and electrons coming off them. They're blowing away the cloud that they were formed out of. And you see these wonderful little structures. This particular sort of finger of a cloud that you see here is about a light year long from top to bottom. And a light year, I think most people know, light travels at 186,000 miles per second. And if you go at that speed for a year, you cover about 6 trillion miles. So that's about a 6 trillion mile little finger of the cloud. The reason it's shaped like that is because there are actually stars forming inside here too. And this is a denser area of the cloud where stars are forming inside, and it's holding up against the wind of heat and light and particles from this newborn cluster of stars. To some extent, forming a star is very simple. The only thing that happens is you have these giant structures in space of gas and dust. And we'll look very closely at that dust in the later part of the talk. Gravity begins to bring together denser parts of the cloud. If a little area of the cloud is denser than others, it brings in more material. When you have clouds that are light years across, hundreds of trillions of miles across in some case, you have a lot of material to draw on as gravity begins to bring stuff together. Until finally there's an area of the cloud that becomes hot enough and dense enough, it ignites a natural nuclear reaction and becomes a star, and that's what a star is. The James Webb Space Telescope has been amazing in studying star formation. For those of you that may know the Hubble image of the pillars of creation, this is a version of that taken by the Webb telescope more recently. And we were able to see these giant clouds in space forming stars. I mean, you can really see, so here's a little star right here that's just turning on. You can see light and heat coming out of that. And there's a little bit of the dust left over that's actually being blown away. Similar to the last picture, the reason there are these wonderful finger shapes is that as clouds nearby make new stars, the stars turn on, all of that heat and pressure blows away the cloud and forms these finger structures on the edges. So one of the main goals of the Webb telescope was to understand better how stars are born. And I love these images. They're so beautiful to me. Sort of honing in on that central finger, you can go a little bit deeper in there. And the James Webb Space Telescope is sensitive to heat light, infrared light. And you can see inside there the glowing areas are where there are these baby stars being formed right now. And I love these images. I mean, these images, in a time of artificial intelligence and computer graphics and all of that, these are real pictures of what the universe looks like. These certainly are modified in the sense that our eye is not as sensitive as the Webb telescope. The Webb telescope sees in heat light, infrared light. But everything you're seeing here is an actual physical measurement. A particle of light hit our detectors. We made an image out of that. And the universe is beautiful. And so I wanted to talk to you a bit about this process of star formation, all of these amazing clouds of dust in space, and how that comes down to be related to us here on Earth. This is a picture of a newborn star just turning on. And again, this is a recent picture from the Webb telescope. This is something that I never thought I was going to see. When I was studying, when I was a student in astrophysics, we would have models and diagrams and artists' conceptions of what a newborn star would look like. It's amazing to actually have a telescope sensitive enough that you can see this. And let me show you what you're actually looking at. The newborn star itself is hidden. It's hidden beneath a disk, a rotating disk of dust. This dark line that you see going through the middle of the image is actually, if you can think about a frisbee, a very thick dust, and it's rotating around this young star. The young star has formed in this cloud of dust and gas. It's drawn all this stuff together by gravity, and some of that material has ended up in an orbit, a disk around the star. When you think about a solar system, like the one we live in, our sun is 99.9 something percent the mass of the solar system. Almost everything collapses into the sun to become the star. That's really what a solar system is. But there's a little bit of schmutz left around, orbiting from the cloud. And that becomes the planets. That becomes what we're made of. Now, what you're seeing here, aside from that disk of dust edge on that's hiding the young star in the middle, you can tell the young star is turned on because it's lighting up gas around it. All of these beautiful structures that we actually don't really understand. We don't really understand why there's this sort of interesting jet of material coming down here. But all that is being lit up by the young star turning on. And then if you see there's two jets coming out, one in this direction and another one that's kind of hidden still in the cloud. These jets are actually hundreds of billions of miles across. And they really show you that a star is turned on. These jets happen when a star is so young the nuclear reactions aren't stable yet. And it jets material off along the magnetic poles of the young star. So in many ways, we're looking right at the birth pangs of a star. This is what a brand new star looks like. And although this process can last for many thousands of years, this is the very, very first time a star begins to shine. Like I said, kind of the birth pangs of that. Okay, now, this is an artist's conception of what happens in that disk. That disk that's left rotating around the star, a little bit of material from the cloud hangs around the newborn star. And from that, over time, planets evolve. Planets form, again, similar. Gravity brings material together. Planets become larger and larger as smaller bodies impact each other and come together. But what we're going to talk about tonight, the one mission I have time to tell you about, is a mission to talk about how we can explore what the chemical nature of that cloud was. What was the cloud that we formed out of really like? Why did it have the right building blocks for life? What did it have in there chemically? Is there a way to see what things were like billions of years ago before life started? And in this artist's conception, one of the things I want you to pay attention to is we certainly have the new star that's forming up here. Think about this as the very young sun. There are planets that are coming together out of this disk of dust and gas. But there's a lot of smaller material that just kind of coincidentally doesn't get put into these bigger planets. And these are the things that end up becoming comets, asteroids, small bodies of rock and ice in space. When you see a shooting star, a meteor coming through the atmosphere is a tiny little bit, could be a grain of sand or a little bit of gravel, a little bit of material that wasn't actually made into a larger body. Or in some cases was part of an asteroid that hit another one, things got kind of pulverized. But we actually estimate that we accumulate about 100 tons a day of this stuff as we go around the solar system, and also the sun is going around the galaxy. As we move around our own galaxy at 500,000 miles an hour, we think we pick up about 100 tons a day of material from space. That formed the planets, that formed everything that we have here. So what was in that cloud, and how did that set the story for how life can start? So these are some of my friends at Goddard Space Flight Center. Goddard, by the way, is a base of about 10,000 people. So it's a very large base. NASA has 10 bases all around the country. Goddard specializes in having the most number of NASA's research scientists. So I worked at the Jet Propulsion Laboratory for about 12 years. JPL has some scientists, but I mean, to me, I think their real specialty is they build the rovers. They build the Mars rovers, they build the spacecraft. They have the most incredible engineers I've ever met. Goddard, which I came to mid-career to be the assistant director of science, has more of our research scientists. And this is our group, one of our amazing groups. I love this term. These are people called astrobiologists. And they're people with doctorates in chemistry or biology. And their job is to think about how the conditions of life start in space and what evidence we have of that. And so this is Barbara Cohen in her postdoc. She's in the middle. And they're holding up some really, really valuable samples of basically rocks and dirt from space, things that fell to the Earth as meteorites. And meteorites are our best samples that we have that are easy to get of these asteroids and comets, these smaller bodies. Some of that falls to the Earth and we're able to collect it. And this stuff is incredibly valuable. We go to great lengths to collect this. These are some of my friends, again, the astrobiology team, although I can't even figure out who is who, because they're in the middle of Antarctica. And they go out on snowcat trains. Actually trains. There's like one part that's your dining area and your sleeping area and your bathroom, and they basically are on these wonderful tractors that take them across the ice sheets of Antarctica. Antarctica is a particularly good place to look for meteorites because any bedrock, any native rock around is a mile under the ice. And so when you find a rock in Antarctica, I mean, it's not guaranteed, but it's a good chance if it's on the surface of the ice sheet that it actually came from space originally. And it's not even, I mean, there's no way you could just aimlessly look around Antarctica for rocks. But what happens is that the glaciers of Antarctica move toward the central Antarctic mountain range. And as they do so, as soon as they hit the mountain range, they drop the rocks that are in them. So there's a place in the middle of Antarctica that you have a good chance of finding meteorites. Now, we don't know how long that meteorite has been sitting there. We don't know whether it's melted from somewhere else, how long it's been transported. It certainly has been contaminated by being on the Earth. There's been water, there's been ices. But even so, this amazing team of astrobiologists over the last 10 years at Goddard has been able to prove that the chemicals they see in these asteroids are actually extraterrestrial. They formed in space. And they do that with looking at very, very delicate abundances of how many neutrons there may be in a particular atom. They do this very, very carefully. And so about 10 years ago, this team discovered that these meteorites had amino acids, the building blocks of our proteins, amino acid molecules. And they could show for the first time that these definitely were from space. They'd not been brought there by the water that the meteorite sat in. I mean, the contamination protocols are so extreme. I mean, seriously, if somebody sneezes, it's a problem. I remember my friend Danny Glavin, who's over here on the extreme left here, he once told me about working on a sample for 3 years and realizing he just contaminated it. So he couldn't work on it anymore. He talked about crying. The 3 years of his work actually doing that. But Danny Glavin and Jason Dworkin and Jamie Elsala, the people that you see up here, are some of my superheroes at NASA. And I was talking to the graduate students and the postdocs at dinner today about how, we were talking about government funding and how to deal with a life in science and science communication. But I had to really sort of reiterate what a joy it was every day to go to work with people like this. People that are so passionate and dedicated and talented. They could certainly be making more money, working for some kind of private industry, but working for NASA was a huge privilege. I mean, every day I got to meet these incredible people. This was actually for an article that was in Nature magazine and also in one of the NASA press releases, and they made them look very serious. And of course, I mean, anybody who's ever been in a laboratory, it's like you never have dramatic lighting in a laboratory. A laboratory has good, it doesn't look like that at all. So, I mean, I took the picture of them, but I made sure I had a real picture over here of what they actually look like. All of these wonderful people that do not look that serious. But they started to find evidence that the building blocks of our life, of our proteins, of our tissues, you find the exact same molecules coming down in meteorites. And you also find little inclusions of liquid water sometimes, or even ices. The liquid water is amazing. Sometimes there are tiny little bits of liquid water in meteorites. And that water, amazingly, had an exact chemical match for the water in our oceans. Little by little, there seemed to be a story piecing together that it maybe isn't a coincidence that the things that are coming down from space have the exact chemical matches that are in our body, in the water, in our proteins. So we decided at NASA, in this case about 15 years ago, to try to return a sample from an asteroid that we could guarantee was pristine, that we knew hadn't come falling in through space, flaming through the atmosphere, falling on Antarctica or wherever, God knows what had contaminated it. What could we find in an asteroid if we actually went there? If we went to one of these small bodies that is a leftover from the beginning of the solar system? You may wonder why it'd be interesting to go to a little rock in space. The reason is that these rocks have basically they're time capsules. They're little bits of the cloud that we formed out of, little small bodies that formed out of that dust. But they didn't get modified by being made into a planet. I mean, everything on the Earth has been modified. The interior core of our Earth has melted everything. There's been erosion and rain and different chemistry on the surface. What does it look like if you retrieve a sample from space that you know is pure, that nothing has changed it for billions of years, since possibly before the beginning of life. And they selected an asteroid called Bennu. And I don't know, can you bring the lights down a little bit in the front? I'm not sure if you can or not. But Bennu is not a particularly large body. It's only about half a kilometer in diameter. And you see here in comparison to the Empire State Building and the Eiffel Tower. Thank you, that's very nice. And we selected Bennu because it's on an orbit that made it convenient. It occasionally swings fairly close to the Earth. And so in order to take the sample, we actually went out more than 200 million miles. But then the orbit of Bennu actually takes it fairly close to the Earth, so we could send back the sample reasonably simply. Bennu also seemed to be very, very dark. We didn't have good images of it. It's a tiny little body far away from us, but it's actually blacker than a lump of coal. And we figured that was probably because it had carbon on it. You know, carbon is the backbone of our chemistry. Organic chemistry means chemistry based on the carbon molecule. And so we figured, hey, a good idea, there's carbon there. It also, I mean, it seems to be rotating fairly quickly in this graphic. It only rotates about once every 4 hours. And so many of the asteroids are tumbling very, very quickly, rotating very quickly. And in order to get a lander to actually go down there and get a sample, you need to match the motion of that asteroid. Very, very difficult. So Bennu as well wasn't rotating particularly fast. So we selected this asteroid to go out to and retrieve a sample. And this is an artist's conception at the beginning of the mission. I'll explain why it's the beginning of the mission. It was a relatively small spacecraft, a little smaller than the size of a car. Very actually inexpensive. It actually came in under budget and on time and all of that. And the idea was that we would go out to an asteroid and basically vacuum up some of this pristine material from space to see what was in there. The mission has one of the worst acronyms NASA ever made. They named it OSIRIS-REx. Osiris is the god of the underworld from the Egyptian mythology. OSIRIS-REx, kind of, King Osiris, but they made that into an acronym, and I did actually talk about this on TV, so let's see if I can still do it. So it's the Origins, OSIRIS, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. There you go. And I can tell you about all of those things. I mean, spectral interpretation, obviously we had spectrographs on the instrument that could tell us the chemistry. Resource identification, I think they were looking for water and things like that on the asteroid. Security, this is actually one of the technically most risky asteroids. It comes fairly close to the Earth. And someday, it will either hit Earth or possibly, more probably, Venus. People never think about that. They hit other planets as well. But a half a kilometer asteroid wouldn't do a huge amount of damage, but it could be a really bad day for a city if that hit it. And one of the things that I was really kind of privileged to be involved in at NASA is we work with FEMA. I'd be happy to talk about this later in more detail, about making FEMA understand how much information we would have on what time scale for a possible asteroid impact. And so we work with them on that. Anyway, so the idea was just happily go up to an asteroid. I mean, these bodies are too small to actually go into orbit around gravitationally. They don't have enough gravitational pull. So you need to catch something that's going like at 30,000 miles an hour. You need to figure out a way to scan the surface and orbit it all by just engine thrusts. The gravity is not going to help. And then find a way to match the motion of the surface, all the tumbling, all of the rotating, and go down and take a sample. That seemed to be a pretty decent problem to solve. But it got more complicated than that. Here was Bennu when we first actually came up close to it. We'd only seen radar images and very, very fuzzy little dots before. We'd never really seen the asteroid in any detail. So we would go all the way out there, in this case about 200 million miles away from Earth. And okay, that looks interesting. The surface looks kind of rocky. One of the things I should mention is that we had designed this little vacuum cleaner to go and vacuum up a sample. We were looking for basically dust. Nothing larger than a dime could actually fit through our vacuum. And so at first we were like, okay, it looks kind of rocky. Then it turns out it was all rocky. We didn't find anywhere that had these small particles. We took 2 years orbiting the asteroid, scanning the asteroid, looking for any little bit, any little impression that actually had these small particles we were after. We had to completely redesign the mission because we didn't find anywhere bigger than about 2 parking spaces in a parking lot. And the spacecraft was meant to just happily go along the surface and suck things up, and that wasn't going to work. And so I have a little short video. I probably won't have a chance to play all of it. But these are the people working on the mission and the problems they had to solve, and I just think this is fantastic.
As we started to approach Bennu from a distance and it started to fill up the camera field of view, it looked exactly like we thought it would, with a few boulders sticking out. But as we got closer, we expected to see a very sandy surface with maybe a few boulders here and there. And what we saw is very little sand. And we saw these mountains, we saw boulders, we saw rocks, and we saw very few areas that had this sandy surface that we were expecting and what we had designed to.
OSIRIS-REx is NASA's first mission to touch the surface of an asteroid. We have never done this before. We're actually going to collect a sample and bring it back down to Earth for further examination by scientists.
In order to achieve that objective, the OSIRIS-REx spacecraft has been navigating around Bennu for about the last 2 years, studying it in great detail, and also overcoming a number of challenges that Bennu has presented. We were looking for locations on Bennu that were 50 meters in diameter, relatively flat, and covered with fine-grained material. And by fine-grained material, I mean stuff that's the size of a dime or smaller. We realized that there were no sites on Bennu that even came close to meeting this criteria. Everywhere we looked was too small and covered with boulders. So we actually had to fly a number of additional close passes over the asteroid and rethink our entire plan for grabbing the sample. After the additional observations of Bennu, we had to down-select to 4 sites, and then go back and survey those sites even further to select the final primary sample site.
My first impression of Nightingale is that's the last place I wanted to go. But as we started looking at other sites, we saw that 1, this is probably one of the most sampleable sites, and 2, we were overperforming in our navigation capability and our ability to contact. Natural feature tracking works a lot like the human mind in that we pick up landmarks along the way. As we descend, we look at features on the ground. We program the computer to recognize certain features. It takes a picture, says this feature is not where I expected it to be, it's a little bit off to the side, updates its position based on where it's pointed and where that feature shows up in the camera position.
The tag event is our touch and go event, which is where we'll actually be retrieving the sample from asteroid Bennu. We start with a series of maneuvers, one of them being the checkpoint burn, which is where we'll actually check our position velocity in relation to the sample site.
And then the match point burn, about 10 minutes later, will zero out our horizontal velocity relative to the surface. And then about 10 minutes after that, we make contact with the tag SAM, fire the gas bottle, and then back away.
And we hope to get at least 60 grams of sample, and then we'll be able to store that and bring it back down to Earth.
But there are several things that could go wrong, and we also have to be prepared that we won't be successful on our first try at Nightingale.
We don't only get one shot at tag, we actually have 3 nitrogen bottles on board the spacecraft, so we can potentially do 3 tag attempts if needed. We go through several what-if scenarios, and this is how we actually prepare for a lot of our contingencies.
So we've had to look all around the surface and identify the rocks and boulders that if the spacecraft were to tip over up to 25 degrees, it could come into contact and be damaged.
We had to develop.
I'm going to stop it there. The thing that's amazing to me, and what was so incredible being with teams that solve problems like this, so you get out to this asteroid, and you got this one chance to sample this asteroid. It's not the way that you thought it was going to be. The spacecraft wasn't designed to be able to guide itself autonomously originally. It wasn't able to sort of see landmarks, wasn't able to figure out exactly where it was to such accuracy. All of that was reprogrammed on the fly, sent up to that spacecraft years later after it was launched. And when the tag, the touch and go sample return happened, it was 200 million miles away, which actually corresponds to about a 20-minute light travel time. So if it's coming down and it sees that there's a boulder in its way, it's not coming down at the right angle. It wasn't designed to have the capability to wave off and say, I'm not going to do that. All of this autonomy was programmed in later when we realized we had to do that. So this incredible, like I said, overperformance, actually being able to guide the spacecraft better than we ever thought we could, take it down to within about a 2 parking space area. It was incredible to see, and so I was actually hosting the event for this sample return, and this is just this is an actual camera from the arm when it came down. It all worked perfectly. This was our first attempt. We didn't actually end up using any of the backup attempts. We broke through the surface, sucked everything up, and then we were originally going to spin the spacecraft to see the mass of the sample we returned, because we wanted about 60 grams. But it turns out that the pebbles were so big, they had jammed open the collector, and the collector was losing material. And so instead of doing that, we just got it immediately all sealed up and sent back to Earth. And there you see a little video camera from the spacecraft as we seal it in this little capsule, and then we send the capsule back to the planet. I was amazed this actually pulled itself off. This was all done during the height of the pandemic. Now, this was done in October of 2020. Flights weren't running. We were supposed to have people in a mission control. We had to break the mission control into 4 different rooms. We had to rehearse everything remotely. It was an incredible time to see a team pulling together, and just a real privilege. So this is actually to show you that we parachuted the sample back. It came to Utah. This particular picture is of a practice session. You can see because the sample canister is actually not very blackened. It would eventually go through the atmosphere and get a lot more burned up. But we didn't have an active picture of it landing in Utah. But this is a real picture of the actual sample canister on the Utah sands and people going out to begin the process of opening it up. I was sent to the Johnson Space Center in Houston. They do all of our samples of extraterrestrial material. And what we found inside was really nothing short of miraculous. So the goal was to collect 60 grams of this material. We collected about 125 grams. And you see here this wonderful black powder that ended up in the detector. So as I said before, this is a sample of our solar system before anything else modified it billions of years ago. I mean, that blows my mind. What was in there? What was in the cloud that we formed out of? And so I'm going to end with this video. I'll show you and give you a sense of what we found, because it is quite amazing.
The origin of life is one of the deepest mysteries in science, but the clues to solving it have been buried by plate tectonics, the water cycle, and even life itself. For answers, scientists are looking beyond Earth to primitive asteroids like Bennu, the target of NASA's daring OSIRIS-REx sample return mission. Now, material from Bennu is revealing a lost world from the dawn of the solar system, with the right conditions to foster the building blocks of life. When scientists examined the Bennu samples, they discovered evidence of a wet and salty past. Among the dark rocks were bright veins of salts that form on Earth when brines evaporate from alkaline lakes. Searles Lake, California is home to a mineral called trona, which is mined as a source of baking soda. Scientists found microcrystals of trona and other evaporite minerals within the Bennu samples, indicating that they once held pockets of sodium-rich water. Such brines are ideal for cooking up organic molecules, carbon-based compounds that are the stuff of life. Bennu is a carbon-rich asteroid, and its samples are chock full of organics, including amino acids and nucleobases. Amino acids can be bonded together in long chains to build proteins, which give cells their structure and function. Life is constructed from a set of 20 amino acids, 14 of which were identified within the Bennu samples. Nucleobases are the genetic components of DNA and RNA. All 5 nucleobases were discovered in the Bennu samples, a first for extraterrestrial material collected by a spacecraft. In addition to organic molecules, scientists found that the Bennu samples are surprisingly rich in ammonia. On Earth, ammonia is a common agricultural fertilizer. It readily evaporates at room temperature, but is more stable in cold environments, like those found in the outer solar system. Bennu is too close to the Sun to retain pure ammonia, so its samples must have formed during a more distant, frigid past. Salts, organics, ammonia. Thanks to OSIRIS-REx, we can now piece together these clues to tell a likely origin story for asteroid Bennu.
I'm gonna pause it there and end, but the amazing thing, Bennu most likely formed in the outer solar system. In the beginning of the solar system, the sun was very hot, and it blew away a lot of the lighter materials like ices into our outer solar system. We don't think there was much water, at least not the surface water on Earth that's original to our planet. Our planet formed so close to the sun it was quite warm, and most of the volatile things like water probably evaporated off. But then over time, these asteroids and comets and smaller bodies brought back water, and with it the organics. All of our nucleobases, all of the letters of our DNA and RNA were found in this meteorite sample. It's wonderful to think that when you go out and you try to piece together the story of the solar system and how life began, in some ways it becomes like this obvious. These small bodies have all the building blocks of life ready to go, locked inside them. You bring them to a planet that's warm like the Earth, stable. You can get liquid water on the surface, and you just have these little bombs of pre-life ready to go. So, I mean, after all of these years of working to see and prove that the ingredients of life come from space, I think that seems more likely than ever. And working with the OSIRIS-REx team was an incredible thing personally, to watch how teams solve problems and to come up with this amazing result that the building blocks of your DNA very well may have come at first from space. So that's just a little taste of science. So thank you so much for listening to that.
Well, thank you, Michelle. That's
Welcome.
absolutely fantastic. So what we're going to do is we're going to have a little Q&A here, fireside chat. Imagine fire, and then we're going to open up the floor to questions that you might have. And so, Michelle, thank you for being here. Thank you for that wonderful presentation.
Thank you for having me. I guess I'm so honored. Thank you.
So I want to start a little bit about your personal story.
Okay.
As I mentioned in your intro, your
Sure.
mother claims that you got interested in the sky before you can walk. Between not walking and looking at the sky to a long career in NASA, there must have been decision points along the way that helped guide your career to where you were. What were some of those?
Well, I mean, it's funny. Sometimes there are decisions, and sometimes there are almost the opposite of that. People often say, "Did somebody inspire you to go into science and inspire you to ask these questions and things?" And the thing about, for some reason, I was interested in space from a toddler. I couldn't tell you why. And I've met people all over the world. I don't know whether you had the same experience yourself, that there was just something about the stars and space that was just intrinsically fascinating. And I mean, honestly, when you think about the fact that most people should be doing more practical things, farming, having children. I mean, my mother was very active in things like civil rights and human rights. She was in some marches with Dr. King. She worked a little bit with Father Grappi in Milwaukee. And so she's this sort of civil rights activist. She has this baby that loves the stars. And she's just like, lights in the sky, right? What? I mean, she's very proud of me. She's actually cat sitting for me tonight, and but I mean, she often says, sort of a benign parasite on society. I mean, I wasn't doing a lot of good, but I wasn't doing a lot of harm. So at least there's that. But there are people all around the world, and I have been all around the world, and you meet people that are kind of in some ways kind of part of your tribe. The space, for some reason, I mean, and so the same is true for music or literature or any field of study. Sometimes you just meet people that just can't get out of their head, and they don't even really understand. And that surpasses any boxes humanity has made to separate us. Whether it's gender or ethnicity or economics or geographically where you are in the world. You meet people that have this fascination. And it's a wonderful privilege to be able to kind of travel the world and tease out who else heard this voice from space. And so yeah, I mean, so my science career was mainly about not being dissuaded from that. I've been told so many times I don't have the personality of a scientist. I'm not driven enough. I'm not logical enough. I'm not linear enough. Not to mention I'm a small little blonde Wisconsin woman, whatever. But the whole thing has been just trying not to listen to that. So in my case, although there have been inspirations and mentors and people that helped, I mean, science education blew me out of the water. I was scared and confused the whole time. I went from Waukesha South High School, a public high school, to Harvard University, and I had a very good time at Harvard in many ways. But I mean, day one from Physics 1, I was lost. I was scared. And a part of my life has been, I just don't want anyone else to have to suffer that way. Science itself, I mean, once you spend a career with it, I mean, certainly it's like learning a language. It takes time. It takes time to, if someone said to you, you need to learn French, that's fine, but you walk into a room where people are screaming French at you, and I mean, that's perhaps not the best way to do it. So I was left behind in my science education, but I love the universe so much. I just kind of kept showing up for the punishment. I told my mom that when they get a restraining order and they won't let me come to the university anymore, then I'll leave. And somehow it never happened. So
I'm glad it didn't
yeah.
happen. Right. And
Well,
we're-
what's your? I mean, your experience with science education. I mean, did you feel? Did you take to it right away? Did you have similar experiences?
My story is probably a little bit like yours. I tell students today that if they looked at my GPA from college, I should be a history professor.
Absolutely. Me too.
Yeah, right. So,
I agree.
not an astronomer.
Yeah,
Right. So I
But you love the science.
Exactly.
Yeah.
It catches you in a way. That
Yeah, I had to take differential equations. I had to take twice. I was going to fail it the first time, so I dropped it. People don't realize that about being a scientist, and this is not uncommon. That people that enjoyed research or science management or science leadership often didn't do particularly well in actual classes. That's an important thing to tell students.
When did you take to science communication? And
Well, so
how that is a passion.
You know, it's funny. It is a passion of mine, and I'm very proud of it. And we were just talking about this at dinner. It also wasn't so much of a decision that I made. When I was a postdoc at Caltech in this would have been the late 1990s, I was just going to become a research astrophysicist. I didn't have any intention of going into science communication. But NASA came up with this requirement that every NASA program had to have an actual approved, organized communications part of the mission. And they just kind of looked for somebody to give this to, and they gave it to me as a postdoc. And they said, "Hey, you kind of like giving talks. Why don't you look at this?" And I mean, this was for the Spitzer Space Telescope, and that was the education budget came to about $1 million a year. That was back in the 1990s, and they just sort of threw it on my lap and said, "Here, do something with this." And for one thing, I've noticed that a lot of times young women get singled out to do the communication. They're sort of like, well, you seem to be people relate to you, you're less threatening. Here, you do the communication stuff. I'm not sure it was what I wanted at the time, but I found it fascinating, and I found it very rewarding, and I think it's very valuable. And so I made the decision a couple years in. I think by the year 2000, I was a senior scientist at JPL, but my specialty was science communication. So it sort of got thrown in my lap. And I that has been hard on my ego because, you know, I go to the American Astronomical Society meetings and I haven't published a first author paper for a long time. I mean, I have in the past, but I sort of sometimes get this attitude about, well, you know, what did you do with your career? You became a science educator, and that seems to be something less. And I try to tell myself that I don't agree with that. I think being a science communication team on a mission is as important as having your thermal engineers or your navigation people. I think being a communication person, you should be absolutely part of the team. But it hasn't been easy personally to get myself in that position.
Got it. But you've been witness to missions. We had a great video.
Oh, well, I've witnessed hundreds of missions.
And it's a great story, right?
That's
you
right.
get through the asteroid, things aren't as they seem, you have to adjust. Everybody there looks calm.
Yeah, right.
Behind the scenes, is there panic? Is there, oh my God, what did we do?
Oh yeah, I mean, it's wonderful to spend your life with people that have this sort of intrinsic optimism that we're going to figure this out. That doesn't mean that it's not painful. My late husband was one of the major engineers on the James Webb Space Telescope, and that telescope had to unfold itself in space because it was such a big telescope it couldn't fit in a rocket unless it was folded up, and there were about 340 commands that, you know, this little pulley had to pull, this little actuator to pop off to get this thing to unfold. And if you had asked me before the launch, it's like bet your mortgage, right, whether it's going to work or not. I would have probably said it wouldn't have. I mean, it was audacious. It was hugely risky. 300 and some commands that were single point failures. Any one of them didn't work, we're done. That cost us, you know, sleepless nights and arguments in the room about what was the best strategy and all of those things. Doing the communication as well. I mean, both for the OSIRIS-REx thing, like I said, we were trying to do communication, and then the pandemic hit, and we were just lost. You know, how are we communicating to each other? How are we going to do this? You know, the day that I was at the mission control, you know, the teleprompter went down in the middle of the broadcast. I just decided, well, it's my show now. You know, I just keep talking, keep smiling. Same thing happened for Webb. The telescope launched in the pandemic. We had this great launch event, but then the next day, one of our crew members came down with COVID, and this is all pre-vaccine. And so they separated us all immediately. And so we were supposed to have press releases, we were supposed to have follow-up television programming. I was in a conference room with a television camera on me. I was literally typing as I was talking to my supervisor saying, help, help. I don't know, do we have another speaker coming? Am I just gonna be talking for another hour off the top of my head? I mean, everything was just in chaos because of the COVID emergency. So yeah, we just keep tap dancing, and just when everything goes down, just realize, okay, now it's your show. Just go. I mean,
just
no
go.
one's going to help you, so just go.
Just do it.
Yeah.
Wow, fantastic. Let me ask one more question, and then we'll open up to the audience. Asteroids. There's a lot of myth about asteroids. There's misunderstanding. There's killer asteroids. You know, Bruce Willis is going to land on an asteroid and save the day.
No.
All of these things about
It's
asteroids.
the size of Texas.
Yes, absolutely. What's the one thing, if you wanted to let everybody know about asteroids, that we should know and be able to take home with us? What?
Well, it's the one thing. I mean, the one thing. The one thing is what I've said. I mean, they're much more in the context of science, a bringer of life than destruction. I mean, yes, that's an aspect to them. But why would you go out, 200 million miles away and bring back a sample? We found out where our DNA comes from. That's the thing. They're this connection to the cosmos. Certainly, assessing the risks of them is a real thing. And as you know, NASA has had missions where we've actually impacted asteroids, where we've tried to divert the path. You're not going to, unlike Bruce Willis, you're not going to blow them up. If you put a nuclear bomb in the middle of Bennu, by the way, Bennu's not really a solid structure. It's all just these rocks that are held together under gravity. All you do is heat it up. You just make it mad. That's all you do. It would still be coming toward us, just a little bit hotter than it had been. So we actually calculated at NASA for the Bruce Willis movie. It's the size of Texas. It starts to enter the atmosphere, and then they blow it up into 2 bits. And it was like the energy output of the sun would have been needed to do that. There was a better movie that year called Deep Impact.
I remember that one.
Which was another asteroid movie, which was far more realistic. But it is amazing to think, yes, it does affect life on Earth. We will be hit again someday. We try to find as many of them as we can. The new telescopes that have gone online, the Vera Rubin telescope, which just went online like 6 months ago, is doing these ultra high resolution scans of the sky every 3 days. That blows my mind. And I think was it last week they released 2,000 new asteroids that they find. So we're finding them more and more. We're getting better at it. But I would say, one thing about asteroids, put the risk aside and realize it's from where your biology comes from. Your water, your DNA, your organics arrived here by asteroid.
Well, we really are star stuff, as Carl's saying.
Well, a whole other thing, the James Webb Space Telescope now has the capability of actually seeing as stars explode, which atoms are created, which elements are created in different parts of the explosion. When I was in graduate school, we'd never seen some of the heavier elements like gold, silver, platinum. Interestingly enough, iodine and bismuth. Iodine we need for our it's in salts. Bismuth is what pepto-bismol is. The only time now we've ever seen those is during the creation of a black hole. When 2 dead stars spiral together and create a black hole. At one point, we saw 10,000 times the mass of the Earth in gold created in just a few seconds. We now have the capability of seeing which stars create which atoms. And this is, by the way, this is all just like pictures. This is not a theory. When you look so far out into space that the light took so long to get to you, light traveling at 186,000 miles per second, it still takes billions of years to get to you from these distant galaxies. We look back to a time when there were very, very few or even none of the heavy elements like carbon and oxygen, calcium, phosphorus, sulfur. These things are only formed in stars, the only thing that makes these atoms. And so, to me, that's my favorite fact in all of science, is that the only thing that makes a carbon or a gold atom or the iron that makes my blood red, it's a star, the core of a star that fuses it, then that star dies, distributes its material into space, and it forms into these disks around stars and comes to us from asteroids.
Fantastic.
It's amazing.
Let me open up to the questions from the audience. We've got a couple microphones running around. We've got a question.
It doesn't have to be about things we've
Question
covered.
up here.
Yeah.
I'll wait for the microphone to arrive, please. And then
Please feel free to ask about anything because, like I said, I've overseen hundreds of NASA missions, been part of the team, so I'm happy to answer questions about anything. Please.
Thank you. I was wondering, when you were trying to collect the specimen from Bennu, how many miles away was it? How long did it take to communicate back and forth to the unit that was doing the sampling? Because, excuse me, I mean, that must have taken a while. It's not like you could say, okay, stop now. By the time it would get that stop command, it might be all the way through.
You're absolutely right. And I mean, some people think we take these things down like joysticks and you can kind of guide it and stuff. So when we actually took the sample, Bennu was at its sort of farthest away from Earth. It was about 200 million miles away. And that was more than 15 minutes light travel time one way. So if OSIRIS-REx had been coming down and seen a rock in its way, and it said, help, not sure what to do, it would have taken 15 minutes for the signal to get to us and 15 minutes for us to tell it, yes or no. And so this was, I mean, this is the whole thing that so impressed me about the mission, was that the spacecraft hadn't been designed to be autonomous. It wasn't designed to actually be able to make decisions. But when we realized we couldn't just skip along the surface and vacuum things up, we had to teach it. We had to change it entirely. We had to give it an autonomous brain and do that all by programming that we were beaming up after the fact when it was already out there by the asteroid. So yeah, it was about a little more than 15-minute light one way when we took the sample. Yeah.
Great. Other questions? Yes, over here. Microphone's on its way.
Thank you for your talk. You've been really an inspiration for me. I ended up studying neuroscience. Not sure why, but thank you.
I love neuroscience.
Amazing too. My question is simple. What is the shape of the universe?
Oh, simple.
Simple.
Yeah, simple one. Yeah.
I've heard that there's the observable universe and the rest. And I also remember from Stephen Hawking saying that it is finite, but without borders. So
Yeah.
is it a sphere?
Eric and I can probably both take this. So these things are always a little hard to say quickly. So let's see if I can make some sense out of this. When we talk about the universe, what we're almost always talking about is the universe we can see so far, and what we call the observable universe. And that means that we're sitting here on Earth, and we have telescopes that can scan the sky in any direction. And we can look out as far as those telescopes can see in any direction. So the observable universe is a sphere centered on us. But that's not because the universe is centered on us. That's just because of our instruments. If you sit here with your telescopes and you look out in every direction as far as the telescope can see, that's as far as we've seen. And that's the observable universe. The universe is not centered on the Earth. That would be a theological problem for me. So I mean, that's just what we call an observational effect. Now, the amazing thing is that our observable universe, we have instruments that can see so far away that we actually see to a time that was about 400,000 years after the Big Bang. And a friend of mine got the Nobel Prize for this in 2007, Dr. John Mather. I've had the honor to work with him most of my career. He actually was able with telescopes, I mean, it was called COBE, and the last one was WMAP, the Wilkinson Microwave Anisotropy Probe. But he actually saw so far away that he was looking at a time when the universe was about as hot and dense as the surface of the sun. Amazingly so. So the idea that the universe was once hotter and denser than it was. I mean, I'm sure we do not understand the Big Bang, the beginning of the universe. We only just discovered the universe was expanding 100 years ago. We have to go with what we can see. And what we can see is this universe centered on us as far out as we can look. And there is this time effect. So we can look out to an area of the universe where the light took so long to get to us. We see it as it was when the universe was still as hot and dense as the surface of the sun. That area is not like that today anymore. It's gone on to form galaxies and stars. So the simple thing is we've never been able to see to the end of the universe. We're limited by not only the sensitivity of our instruments, but we're limited by time. The farther out you look, the farther back in time you look until the universe becomes opaque. The universe becomes so hot and dense you can't see through it anymore. And that is a sphere centered on us. But that's not because the universe is centered on us. That's just because it's how far we can see, and it's a time delay thing. We have no idea how big the actual universe is. We don't know whether there's a shape to it or not. There may be. I have sort of just kind of a philosophical problem with anything being infinite. You know, I mean, when we were little creatures, we thought the forest was infinite, then the ocean was infinite, then the sky was infinite. The problem is, how can we find evidence? I mean, how can we find something that, you know, even looking back in time, we're looking so far out, we're getting out to the time of the Big Bang. How do we see further than that? We may not be able to. You know, there may be things like quantum entanglement that help us with that, or gravitational waves, but that's kind of a limit that we're at. It's a huge misconception, and one that, being in science communication, I just can rip my hair out. The idea that the universe was tiny at the moment of the Big Bang. The universe could have been infinite at the moment of the Big Bang. It's just that, you know, the part that we see, we have evidence was once in a small volume, but the universe itself could have been, again, we have no idea. I mean, if you think about the universe being shaped just like me, you know, a tiny little atom of mine blew up to become the universe that we know, but there's no evidence of what the underlying original shape was. We certainly don't think the Big Bang came from nothing. The problem is we don't have the physics yet to actually explain what it was like when the universe was that dense and hot. And that's not unusual. We don't have the physics yet to describe what happens inside a black hole, and we study black holes all the time. Even more than that, we study these dead stars called neutron stars, and these are not even black holes. They're sitting there. They're real things. We study thousands of them at NASA, and we don't have the physics to explain how their interiors work yet. So the idea that we don't have the physics yet to describe something, you know, that's going to keep getting pushed out. We're going to get better. We're going to get better explanations. Someday, I think we will understand why the Big Bang happened and what came before it. But we're limited by how far we can see, and we're limited by this time effect. The farther out we look, the farther back in time you look, until you're out to the Big Bang. And then you're looking at something you can't understand. Does that make sense? Yeah. Okay, yeah. Yeah.
Other questions?
It's a hard thing to talk about, yeah.
We've got one here.
Yeah. You should jump in, by the way, if you have
that
any.
was fantastic. Thank you.
Hi, I'm an astronomy student here, and I was just wondering if you had any advice for students or just anyone in general that's like, I'm really interested in astrochemistry, so, and like the reason I'm here is because I was really interested in the OSIRIS-REx mission.
Yeah.
But do you have any like advice for students who are kind of interested in this path of
Well, we just talked about the fact that, you know, don't be discouraged if some things are, you know, harder and confusing than other things. You know, I didn't do particularly well in my undergraduate education. The other thing is that I've had a real benefit in life of paying attention to what groups of scientists I felt seen by, safe with. You know, I mean, I loved astronomy in general, and the reason I chose the group at Georgia State University that I did my doctorate in is I felt that the professors there were really interested in their students. I felt very comfortable working with them. I loved my advisor. You know, I mean, obviously graduate school is a time where you're working very hard, you're not making a lot of money. It wasn't my favorite time of life. But, you know, I allowed a lot of my career decisions as to where I took jobs and even what I studied to be guided by the people that were there. And some of the bigger professional mistakes I've ever made in my life is when I was working for a person that was very bullying and hard to please and kind of a toxic person, and I thought, well, I'm a very hard worker, I'm just going to please them. And, you know, other people would come and go from that group really fast because there was a toxic environment. They'd be there for a few months, then they go, hell no, and they get out of there. And I sort of stayed there longer to try to please this person, but that never happened. You know, finding people that value you and you feel comfortable with is a really good guide. As discouraging, I mean, even when I was getting my doctorate in the 90s, they kept saying, you know, you'll never get a job, there aren't any jobs in astronomy. Mm-hmm. Everybody got a job. It might not have been exactly the place or the position we thought we would have, but when you have a science degree, you have a really useful set of skills. You're not going to be unemployed. It's not going to be wasted, even if you end up not going into professional academics. One thing that I find in universities a lot is that there are lots and lots of other jobs in astronomy that don't involve being a research professor and being like what they call a PI, a principal investigator, the head of a NASA mission. Those are usually professors at universities. So NASA builds the spacecraft, we calibrate all the instruments, we have teams of astronomers that deal with the data. We also can apply for time on the telescope, but we apply with everyone else. Like, I can apply for time on the James Webb Space Telescope, but even though I was part of the team that helped build it, I apply with everybody else in the world. But you still have these jobs at NASA and at other places where we hire hundreds of astronomers to run these missions and to help us with that. And I think sometimes at universities they sort of downplay that aspect of the career. Being a research professor is wonderful, but there are lots of other things to do in astronomy. And the Hubble the Space Telescope Science Institute in Baltimore, we've got a couple hundred people working on the data coming from the James Webb Telescope. Some of them make observations of their own if they win that time. There's a lot more diversity in the career than sometimes I find universities tell you about. But all I can say is that despite there certainly are hardships and times in my life that are difficult, and I am so glad I stuck to astronomy and to what I loved, even if the education was hard. The people that I worked with, the fascinating, joyful, kind people that I've worked with, have given me a wonderful life. So curate your life. You get to decide who values you and who you feel comfortable with. Absolutely.
Great advice. And I want to plug in, you may not know this, we have the Wisconsin Institute Center for Origins Research, WICOR. I don't know if you're familiar with that. When I was in high school, I wanted to do astrochemistry because I liked chemistry a lot more than I liked physics. And then you couldn't really combine the two, but now you can. So seek out WICOR. And there's some amazing people, I think the kind of people that you're talking about, who are working in WICOR, and they will help you.
And you're at one of the best universities in the world, of course. And it's a big university that has its own challenges. I think that going to a slightly smaller university, my professors got me involved in research very quickly. That's sometimes harder to do at a big university, but I highly encourage that. NASA has internships specifically for college-age people. At Goddard alone, we have about between 400 and 500 every year. And those interns are incredible. They get right in with the teams. They do the research. They make the personal connections so that now you have friends in the field and you get to see what the real life of a scientist is, opposed to the classwork. I would highly recommend applying for a NASA internship.
Maybe let's take one more question. Do we have one from the audience? Way in the back.
I was supposed to say just one more. We can, yeah.
If you can stick around,
I can stick around, absolutely. So.
But I want to be mindful of what we promised on the time.
Absolutely, I get it. Yep, people got places to go, cats to feed.
I was wondering if you could help me understand. So, the way I understood it, you were trying to scrape the surface of Bennu because it was going to be a very pure sample of what the universe was previously. If Bennu was flipping through the atmosphere at all this speed, why isn't it picking up a lot of contamination along the way so that the surface would not be pure?
Well, it's certainly not going through the atmosphere of the Earth. That's the main thing, right? So the main thing about samples that arrive here as meteorites is that those rocks come burning through the Earth's atmosphere. That modifies the surface quite a lot right there. Then they end up landing on the ground. And the second it hits, it's like the 8-second rule with the cookie, right? There's bacteria all the hell over that just immediately. So certainly the surface of Bennu, out in the vacuum of space, it's not going to be modified by any air or any chemistry like that. It will be modified by the solar wind. The solar wind is a wind of high-energy particles coming from the sun, and this is actually one of the ways we can prove that those molecules are extraterrestrial, because they're embedded with high-energy particles the solar wind would have actually delivered. The solar wind probably does break up some molecules on the surface. So even the fact that we found intact nucleobases, like I said, all of the letters of our DNA and RNA, that's just very encouraging, because the solar wind probably breaks some of those up. So stuff sitting on the surface of an asteroid is modified by the environment of space, but it's not modified by the organics and the biology of the planet. And that was the main goal, that anything we find in there we know is extraterrestrial. So, so finding all of the nucleobases, interestingly enough, we found nucleobases we don't use. So, if there's life on Mars that has its own genetic code, there could be nucleobases that it's using that we don't use in our biology. Another thing that if anybody's a biology fan, one of the other experiments that Bennu was doing is, do you know about chirality, the handedness of molecules? I don't know whether you do or not. Don't worry about it. We're basically trying to explain how, why the biology on Earth is the way it is. And we're finding that in asteroids, there's far more options. A carbon-rich asteroid sample will have far more, like maybe 50 to 100 times more organic molecules than I use. So, if there's life elsewhere, it could be using a different chemistry. And the amazing thing is that asteroids may give us a sample of what these totally different chemistries could be like. So, when it's in space, it's certainly modified by the radiation and the particles from the solar wind, but it's not modified by water or by chemistry or by any type of melting or plate tectonics or all of that. So it's as pure a sample as we can get. Yeah, it'd be great to kind of drill more down into these asteroids. But we certainly, I should know offhand how far it got into, because it turns out that Bennu was kind of like a bunch of, a ball pit is what we said. There's sort of all of these little balls of material, but they're not really, they're held together with gravity. So we kind of punctured through a crust, and then underneath it was sort of all this mixed material. But great question, thank you.
So I will finish with one question.
Yes, sure.
The next 5 to 10 years, what is the discovery you are most looking forward to?
Oh, lordy. Well, my entire career at NASA, I've really been looking forward to the idea that life has existed outside the Earth, and we're getting closer and closer to that. There was a very important and unfortunately kind of brushed over discovery at NASA about 2 months ago, where on a Mars rock now, we're seeing these structures that we don't have any other great explanation for other than that it's a fossilized bacterial colony. We find these things on Earth, and because we know that there is life on Earth, we say, look at that, billions of years ago, that must have been a cluster of bacteria. And we're starting to find those now on Mars. And so, is it 100% sure that there was life on Mars? I would say probably no. But we're now getting to samples where we can't think of anything else it could be. We're like, okay, what is that? We've got to think of some other explanation beside life. And there's been a lot of controversy at NASA. The James Webb Space Telescope is powerful enough. It can study the chemistry of the atmospheres of planets around other stars. That's amazing. And that's another thing I never thought I would see in my lifetime. And we are now finding exoplanets, planets around the stars in the sky, and they have things like water, methane, oxygen, carbon dioxide, and there was a possible detection of a molecule called dimethyl sulfate. And dimethyl sulfate is very interesting because it's one of these things that we really only know it to be produced by biology. It's specifically produced by plankton. And so, all of us were sort of like, it's like, holy cow, did we just see the chemical marker of plankton? And we're not sure. We need to go back for better observations. And it will probably take this next new observatory called the Habitable Worlds Observatory. But we're starting to get these little interesting snippets that at least internally at NASA, we're all kind of debating, happily with each other. It's like, is that really what I think it is? Or could it be something else? I really hope by the time young people get to graduate studies and PhDs, we may actually have chemical evidence of life outside the Earth. We're not talking about something about civilizations. I'd love to find that too. I work with people from SETI; they're wonderful. But I think hopefully whether it's on Mars or a moon of Jupiter or Saturn. Interestingly enough, Venus as a possible marker of bacteria in the atmosphere. Again, not proven. I think we're close. I really, in my lifetime, I've got a bottle of champagne chilling. It's been there for 15 years. But one of these days we're going to have something that causes me to say, yeah, we just found life.
Fantastic.
I'm looking forward to that.
Great. Well, thank you, Michelle. Wonderful having you here.
Thank you so much.
Thank you. Fantastic. And thank you all for being here. And I hope you take advantage of other Wisconsin Science Festival events over the next couple of days. Enjoy. Have a great night. Thank you.
If you had questions, I'm happy to stay around for a little while. So please come on up. Thank you so much, Eric. Thank you.